Okay, welcome to Lecture 8 of our class. And I'm going to lower it a little bit so I think we can see the screen a little bit better. Hopefully that's not still, can everybody see the screen reasonably well? So here we are in Lecture 8. We're going to be talking about entropy rates, primarily of hidden Markov models, and we're going to start coding. I also want to make sure that everybody's keeping track of our midterm, which is going to be a week from Thursday. That will be held in class. And will include all of the material that's basically now being assigned here. So there's a little bit of new reading. There's chapters 4 and 5 in our book. And in some sense, we've already started chapters 4. But we're also going to be covering chapter 5. And we'll be discussing some of the material of that today and Thursday. And a little bit of next Tuesday. We'll also have a review next Tuesday. A reminder that homework 3 is due tonight via our Dropbox. Homework 4 will be out either tonight or tomorrow. It will be again due next Tuesday night. And we'll include some material from today's lecture, some from Thursday's lecture, and maybe 1 or 2 problems from some of the stuff we'll talk a little bit about on Tuesday. And just to let everybody know that the midterm will include maybe some of the stuff that we talk about on Tuesday, so you'll have 2 days to understand that material. But I will, again, remind everybody that we do have office hours on Tuesday afternoons from 4:30 to 5:30, and if you can't make it physically, you can come there virtually. And also I will gladly have, in fact, probably what I'll do is I'll open up some evening office hours next Tuesday night, and maybe even a little bit of next Wednesday night. So if you're at home, sitting on your couch, watching the latest episode of Breaking Bad or something, I don't know, does anybody watch TV? Nobody watches TV in our department, do they? We just work, right? We don't have any fun. I don't have any fun, I should say. I should speak for myself. But in any event, if you want, you can take advantage of virtual office hours in the evening next Tuesday, and probably Wednesday as well. So again, just to make sure everybody understands, I don't want any confusion about this. We have a midterm that will include material up to including homework 4 and today's cumulative reading. So that means that the reading that's assigned today will be, chapter 5 will be the last chapter that's on the midterm. Okay, any questions about what's going to be on the midterm? At least what you're responsible for? So now you know to start studying for that for next Thursday. Although this isn't an undergraduate class, so you don't care about midterms, right? No. Yeah, to a lesser degree. All right, I'll stop with the jokes. I'll just get to the material. Okay, so a little bit of review. So remember about an MN code. And again, this is sort of this notation that we're using to refer to a series of codes, right? Where there are M code words, and that corresponds to the number of actual words. So there's 1, 2, all the way up to M code words. We have N source symbols, 1, 2, all the way up to N source symbols. And what an encoder does is it maps one of these length N source strings to a length M bit string. And we have a rate, which is log M over N. So this is the MN code. Or we can also sometimes write it as 2 to the NR N codes, because if we're at a given rate, that's 2 to the NR. And all that basically does is the 2 to the NR basically cancels out the N in the denominator, and then the 2 gets rid of the log, and it's just an MN code. So let me just write that. So we often will see this as things like 2 to the N R N, right? That's sort of an implicit rate. It's really the same as M. Did you have a question? Or did I see your hand up? Scott? Scott, yeah. Okay, I thought as I was turning down, I thought I saw your hand go up. Now I'm turning back up, and now your hand went down. So okay. Laughter. See, it's funny because like when I don't try to make a joke, you guys laugh. And when I try to make a joke, you don't laugh. I don't know. I don't get it. All right, so no, I do get it. That was a joke. So of course you didn't laugh. You see. Right, so we had the definition of fixed length block code, where we had an encoder function and a decoder function, and a probability of error. And essentially that's what we want. So basically it's saying that, zooming in a little bit on this probability of error, that when we take a bit string here, or we take a source string here, encode it, and then decode it, and we compare it to the original thing, if it's not equal, then we get an error, and we essentially are asking for the probability over all source strings such that we experience this error. So it's a very natural definition. And then the universal block rate R block code basically says that, if the block lengths get long enough, at some point the probability is going to start going down to 0. And we can make the error as low as we want, as long as the block length is big enough. And as long as the entropy, of course, critically, as long as the entropy is such that we're not trying to code at a rate below that entropy. The rate has to be no less. Sometimes it can be at the entropy, but it really depends. What happens at the entropy is very dependent on specifically what happens. And we'll talk a little bit about this. We'll talk about, when we talk about today, actually, I think we'll talk about one instance where we can actually set the rate to be equal to the entropy. But again, that it's very, what actually happens there at that point is very specific on each individual type of coding. What we're talking about here is more sort of a theoretical thing, which just says as long as the rate is strictly above the entropy, what Shannon proved, and that's what the main theorem is, that there exists a sequence of to the nrn codes, universal, actually, that have vanishing spot probability of error as long as it's the case that we don't try to code less than the entropy of the source. And Q is the source entropy. And this is in the IID context, meaning the source is assumed to be IID, but we also can talk also about stationary ergodic stochastic processes. And so we mentioned the idea of, we've talked a little bit about stochastic processes and what, in fact, would the entropy rate even correspond to in that case. And that, in some sense, really corresponds to like the average novelty per symbol. And that's a couple of definitions. Actually, I expanded a little bit the notion of the periodicity of a state. So there's a little bit more stuff on periodicity that we'll refer back to. But one should understand from your stochastic processes class what periodicity is. And but the entropy rate of the stochastic process can be defined in these two different ways. And one way, it's sort of the limiting residual or novelty. I think of this as kind of like novelty. The residual, the limiting novelty of the next symbol as given the previous symbols. You can also think of it as the average entropy, just by taking the entropy of a set of symbols and divide it by n and see how that limit goes. And what we saw is that for stationary stochastic processes, these guys are the same. And these are just, again, like I said, these slides, everything in the review section here, everything will always be slides that we've seen previously. Okay, so the last thing that we did last Thursday was talk about a very specific case when we have a first-order stationary Markov chain. And remember, in a first-order Markov chain, basically, if we've got the random variable at time n, then the probability distribution of the random variable at time n plus 1 is independent of everything before time n. So time n plus 1 is independent of everything before n given time n. First-order Markov. And in such case, then when we look at this limiting entropy, right away the conditional entropy is such that once we've got the previous random variable, we can essentially cross off absolutely everything except for the preceding one. So we end up getting really the entropy of n given n minus 1, which is this. Right? And so then we get this limit here, but then that's equal to, since the stationary condition, the entropy of x2 given x1, and it really doesn't matter. It's the entropy of any time given the previous time. And so that should, quite naturally be seen to be a function of two things. One is the sort of the stochastic transition matrix, which is given by these guys, and then the stationary distribution. Because all there is really to know about the statistics of a stationary Markov chain is what's the transition matrix and what's the stationary distribution, and this transition matrix is such that the stationary distribution is the left eigenvector of that transition matrix. We know that from theory of Markov chains. So there we have it. And one could essentially look at it in the case of binary entropy, where the conditional entropy is just given this way. So it's kind of like the average of the entropies. Okay, so now we move on to new stuff. So in some sense, what we're going to do is we're going to look at the Markov chain in the context of a random walk. And we're going to assume it's an irreducible and aperiodic, meaning that D, the period of all states is going to be 1. And so that means that there's a unique stationary distribution that comes from the theory of Markov chains. It also means that the self-transition is going to be 0. So what is a random walk really? So basically you've got a graph. And what is a graph? Everybody knows what a graph is, right? Okay. Graph, we've got a set of nodes, or a set of vertices if you want, and a set of, they're weighted. So if this is vertex I and this is vertex j, then basically this edge is labeled with Wij, which is in some sense the weight between these two particular vertices. And the weights are strictly positive, or strictly non-negative, I should say. They could be 0, which basically means we don't draw the edge. And we can essentially do a random walk, where basically we start at some node, say I, and we want to decide randomly which next node to jump to. So we're just jumping around on the graph, on the vertices of the graph. And the probability of choosing the next vertex is basically based on a probability which is proportional to the weight. And for it to be a probability distribution, we use this probability here. Okay, and where Wi is just the normalization constant. We're just sort of essentially summing over the outgoing edges, or we're summing over the edges that are incident to a given node. If the node is I, then we sum over all nodes j. And if some of them are not there, it doesn't matter, their weight 0. And so we're going to guess that a stationary distribution then is going to be proportional to, in some sense, this edge incidence value, Wi. Right? In some sense, like Wi sort of can be seen in 2 ways. One is sort of like the sum over all of the edges that are incident to a given vertex. So just to make sure this is clear, we've got a vertex here. And we have all of these edges that are incident to that vertex. That's how you should be talking about this. Those are the edges that are incident to that vertex. And that corresponds, on one hand, to the distribution over what next set of vertices we might likely jump to. But it also corresponds in some sense to how much inner strength there is to that vertex, because all of those other guys, its connectivity sort of corresponds, once everything sort of settles down and we get to a stationary distribution, it corresponds to sort of how likely we're going to get back to that vertex, right? And if you're, say, a hub, if you're like Graham Central Station, which is, I believe, a station in New York City, you have lots of connectivity to you, so you're likely to come back there. Whereas if you are the train station in Winnemucca, Nevada, does anyone know where that is? Neither do I. In fact, I don't even know if that place exists, but let's assume it exists. Then, no, it does exist. It's not a high connectivity. And so therefore, it seems reasonable to guess that the stationary distribution is proportional to this connectivity value.
Are we assuming that it's symmetric? Wij equals Wj?
Yeah, let's assume it's symmetric, just to make things simple. Let's just make that. In fact, we need that assumption in the bottom case. So basically, if we sum over all of the upper diagonal weights, which is here, then we're going to get that the sum over these connectivities is going to be 2 times, in some sense, the overall network energy, if that makes any sense. And so our stationary distribution, let's guess that we just sort of normalize by the network, the network energy. It's going to be this. Now, it's the stationary distribution for the following reasons. I mean, we can actually prove that this is stationary by essentially plugging it into the condition for stationarity, which is the left eigenvalue property. And what this is saying is that we need, so this is just saying for all j, and this is sort of looking at the before and after distribution. So the after distribution is going to be this, and if we put in the before distribution, which is this, we just sum over, this is sort of the left eigenvalue case. And so mu I, this is the hypothesized stationary distribution. This next thing here is the transition probability. Right? We just cancel things out, and then we get mu j. So therefore that is the stationary distribution under that basic property of this, you know, that's based on that definition of the transition matrix. And in some sense, this is sort of, you know, in some sense robust because the stationary distribution really involves, in this case, or I should say it doesn't involve those edges that don't include I. Right? So that doesn't really change the stationary distribution. The edges, as long as we keep the overall sort of network energy the same, we can sort of mess around with stuff over here, but our stationary distribution is the same, which basically sort of consists of our intuition that how likely that we are likely to come back to this vertex depends on how I'm connected, or how that node I is connected to the network. You know, is it a hub or is it an outlier? The chain is aperiodic, and this is just sort of showing the aperiodicity. And I don't think we need to get into this right now, but you should go over equations 8.4 and 8.5. The thing I really want to get into is sort of the entropy rate. Because in some sense, we want to say, okay, now we've got the stationary distribution, we've got this Markov chain. How much novelty, how much new stuff, or how much surprise is there, on average, in this random walk upon every jump, in some sense? I mean, remember, it's on average. And so we look at, it's a first-order Markov chain, and we look at the conditional entropy, x of 2 given x1, and then we can actually plug these quantities in. So this is just plugging in the conditional entropy according to our definition of conditional entropy for the stationary distribution mu that we know, and the transition probabilities Pij. So let's just write this in a couple of different ways. First of all, what we're first going to do is write it just by plugging in the definitions of the stationary distribution and the transition matrix. Next, we're going to cancel a bunch of stuff out. Like, for example, we see all sorts of things that can cancel. The wi's can cancel. And so we get this definition, or this version of the expression. Next, what we're going to do is multiply numerator and denominator by 2w, which is multiplying by 1. And what this is going to allow us to do is sort of split this into, you know, 2 log terms. This is a common trick that's done. And so once we've done that, we've split it into two terms with a log, this one here and this one. Right? But now, what's interesting about this is that they're both probability distributions, right? So on the one hand, when we sum, let's zoom in on this second one first. So we can sum, when we take the sum over j here, and this j, this whole thing is going to turn into the sum over I of wi over 2w times log. Right? And so therefore we can write this as a difference between two entropy terms. the first guy is this entropy term, and the second guy is this entropy term. And now when we look at it, the first entropy term is over, in some sense, an alphabet size consisting of all of the edges. The second entropy term is an alphabet size consisting of all the nodes. The second entropy is kind of like a node or vertex concentration entropy. The first one is kind of like an edge concentration entropy. Or another way to write it is like the first one is like overall edge uncertainty, and the second one is overall node uncertainty. And I guess I should also mention that the node uncertainty or the node concentration term is for the stationary distribution of the Markov chain. So let's see if that makes sense then intuitively. I mean, so the entropy of the stochastic process, or the entropy in this case of the random walk, is like the overall edge spread or the edge variation or the edge lack of concentration minus the overall node uncertainty. So now let's think about this. So as the node entropy decreases while keeping the edge uncertainty constant. So that basically means the network in some sense is going to become more concentrated, right? So why does this make sense? So now think about this for 1 second. So the edge uncertainty is staying the same. Sort of the overall spread and variation of all of the edges is going to stay the same. But now what's happening is that I'm becoming more concentrated on some of the nodes. Like my certainty about being in this node versus this node versus this node staying the same. This is saying that the overall entropy is increasing of the stochastic process. Now why could that make sense? Intuitively. The reason is, I mean, it seems counterintuitive at first, because you say, wait a second, as I become more certain about the nodes, shouldn't that mean that I'm more certain about the overall stochastic process? And it turns out, no, it's actually not the case, because, you know, when you say that the vertex concentration is increasing, meaning the entropy is decreasing, you know, while keeping the edge uncertainty the same, what's happening is that I'm getting a small number of hubs that are going to become very likely to be revisited. Okay? So when I revisit that hub, the incidence degree of those vertices on average is going to become much, much larger, because the edge spread has to be the same. Edge spread is being fixed. So basically I land at Grand Central Station, but I've got a billion possible connections. You know, from Grand Central Station I can go anywhere. So where is the person going to go? Well, there's this huge distribution of possible places, so I have no idea where the person's going to go next. Hence, the overall entropy rate of the stochastic process increases. That's how you reconcile this initial seemingly counterintuitive concept. So the second bullet point is basically saying that. In such case, you know, we've got a very small number of well-connected hubs, and also it's more likely we're going to land on those hubs in a random walk, and so we're going to be faced with a wide variety of choice. So again, I think that if you were beforehand, before doing this analysis, if I were to say, well, knowing where you're likely to go next on average from a given starting point, where you increase the certainty about where you are, it's saying, don't you think that if you increase the certainty about where you are, you're also going to increase the certainty about where you're going? And the answer to that question is no. So it's only through this analysis does that show you that this is the case. Now, if we look at the last bullet point, it's basically saying if the node entropy goes up with fixed, again, edge entropy, then basically in some sense Winnemucca, Nevada becomes Grand Central Station, right? Every vertex in some sense becomes hubbish. That's the technical term, hubbish, hubbable. We hubify all of the vertices. And in doing so, we increase the overall uncertainty of where we are, but we decrease the overall uncertainty about where we think we're going to go next. That's what the equations say. Okay, so any questions about that? I think that's pretty cool. You can tell when I think things are cool, right? So. Okay, now we're going to talk about hidden Markov models. Raise your hand if you know what a hidden Markov model is. Okay. Very soon, everyone will raise your hand. So, hidden Markov model really is a probability distribution over two n random variables, where n is a variable itself, but it's a class of probability distributions over two n random variables that factors in a particular way. I should change this wording. What I really mean to say is it's a class of distributions over two n random variables that factor in a particular way. There are a lot of different ways of depicting it. One way is to use a graphical model, which basically you can look on the left, which is the Bayesian network point of view, or look at the right. Basically, let's just look at the right because it's a little bit simpler. Basically, the separability property of the graph tells you precisely the conditional independent statements amongst the collection of random variables. This is a hidden Markov model. So we have two sets of random variables. The first set of random variables corresponds to a first-order Markov chain. So this first-order Markov chain says that, for example, y3 is independent of y1 given y2. And y4 is independent of y2 given y3. And in general, the first-order Markov chain has, in some sense, separability properties in a graph. It's basically saying that if I were to take any set of variables here, like 3, 4, 3, 4 separates 5 from 1, 2. Therefore, y5 is independent of y1, 2 given y3, 4. Because it's separable, it's independent. Another instance of this is y2 separates y5 from y1. I've got all this stuff in between. The fact that I'm not conditioning on y3 and y4 doesn't matter. y2, I should say y1 is independent of y5 given y2. So that's also an independent statement that's stated by the graph. So hidden Markov model, a Markov chain. Now in a hidden Markov model, we've got all this stuff. We've got the x's as well, and so and basically what this is saying on the one hand is that that x3 is related to everything else in the graph via its sort of corresponding Markov chain variable. So it's saying that y3 renders x3 independent of, say, x1. Right, so that's a valid statement. So x1 is independent of x3 given y3. And any separability, anything that the graph says in terms of separability, is a conditional independent statement in any corresponding probability distribution corresponding to an HMM. Okay. Now, one thing it doesn't say is that x3 is independent of x1. That is not a valid independent statement. Why? Because there's nothing to separate. Nothing is, when you don't condition on anything, nothing is independent. So there's only conditional independent statements in a hidden Markov model. There's not marginal independent statements in a hidden Markov model. The graph states that, and the probability distribution state that as well. And any probability distribution that abides by a hidden Markov model doesn't require there to be a corresponding independent statement. So that's a hidden Markov model. So it's a family of probability distributions. Now, it's also a sequential process, right, in some sense, because you can say, well, in a first-order Markov process, you can say, okay, well, every time there's a new y, like yt plus 1, yt plus 2, how much entropy, what's the average entropy rate of that stochastic process? What if we're, in some sense, only seeing the x's? The reason why it's called a hidden Markov model is because we don't actually get to see the y's usually. But it was just assuming that there is some underlying Markov chain, but the only thing that we actually observe are the x's, because the Markov chain is sort of hidden. It's hidden from view. So we have this stochastic process which really consists of the x's. And in the context of this class, we're interested in computing the entropy rate of just that process, the x's, under the assumption that there is some y, but we don't know what that is. It's sort of like, again, it's a known unknown, or it's presumed to be a known unknown. And we're going to assume, for the purposes of analysis, that y, the Markov chain, is in stationary condition. So we already know how to compute the entropy rate of that. But again, it's not going to be the same as the entropy rate of the x's. So another way of actually looking at this is that the stochastic process x of 1 through n is a sort of a random function of this Markov chain. So basically, you can think of it as by saying x of I, which is a random variable, so is sort of a doubly random function, right? Because it's, you know, any random variable that's a function of some other random variable is itself a random variable. But what if I said, okay, I've got two sources of randomness. I've got a vat of functions here on the left, and a vat that when I pick out something from the other vat, I get a random value. So what I'm going to do is I'm going to pick a random function and apply it to a random value. Right? And then the next sample, I'm going to pick another random function and apply it to a random value. So it's a sort of, in some sense, there's two sources of randomness. And so in a hidden Markov model, the x's, the random variable x's, comes from these two sources of randomness. On the one hand, y, corresponding yi is a random variable, but also what I'm going to apply on that random variable to get the value x is also random. So that's what all of this stuff really means here. Two vats of randomness. Can't you just imagine big vats of randomness in the world? Okay, never mind. All right, no more jokes in this class. You officially, guys, you guys don't get any more jokes from me for the rest of the class. I will not joke anymore. Actually, I will joke. It's like I somehow can't lecture without making bad jokes. So
does P depend on yi?
It absolutely certainly can. So the probabilities themselves can also depend on yi. Yes. The only thing that can't happen. So that's actually a really good point. The only thing that can't happen is once I know yi, nothing else in the Markov chains matters. So I've got yi, everything else is, you're rendered anything else conditionally independent. The other x's that we've got for different times, the other y's for different times don't matter. So everything is conditionally, the xi is conditionally independent of everything else given the yi. That's the only thing that you can't do in a Markov model. So it's a stochastic process. We're thinking of just the sequences of x. It's a stochastic process, but it doesn't form a Markov chain in itself. Why is that?
Because knowing x doesn't break the.
That's right. Let's go back to this picture. If I'm interested in the distribution, what's the probability over x4? If I condition on x3, does x3 render x4 disconnected from anything else? No, it doesn't. So x3, it might tell us, it might reduce the uncertainty about x4. And it almost, remember, conditioning always reduces, or you can't increase uncertainty. So it will, hopefully it will reduce the uncertainty, and probably will, but in general it doesn't render it x4 independent of anything else. So knowing x3 doesn't help you. Whereas if I know x4, if I know y4, then suddenly x4 becomes separated from everything else, and nothing else matters. So if I just think of it as a stochastic process on x, even if I condition on everything up until time t, like if I know x2, x3, and x4. Is x5 separated from x1 given x2, x3, x4? No, certainly not. So x1 could still be critical for determining x5 given x2, x3, x4. Could be. So therefore, it's not even an nth order Markov chain. The x's. Okay. So everybody knows why now, right? Well, because it doesn't satisfy the first order Markov assumption, or any order Markov assumption. Okay, so on the other hand, if y is stationary, then is x stationary? What do you guess? I mean, don't try to prove it. Just let your deep consciousness, unconscious intuition answer this question. Don't try to start driving it. What do you guess? What's your intuition? This is what you need to learn how to do as scholars, and in graduate school, everyone should learn to, before you start going through pages and pages of algebra trying to prove something, one should sort of have some deep intuition as to whether you think it's true or not. It's our quest. It's still my quest.
It's not necessary. Doesn't seem.
You don't think it's necessary. So somehow you could have y being stationary and x not be stationary.
I mean, you could have like a conditional distribution which is uniform, independent of x, but that would still be in a Markov model.
Okay, let's see if we can answer this question. Turns out the answer is yes. So if y is stationary, then x is also stationary. And the intuition, in some sense, again, rests on this conditional independence assumption. If I know y, then nothing else matters. So if I have a probability distribution of y, and if y is stationary, then in some sense the distribution on x is sort of that mixture. And remember that the functions of this stuff here, this stuff down here, let me just get a pen here. This stuff down here, while it can depend on y, it doesn't depend on t. It doesn't depend on what time you're at. So it's not time inhomogeneous. Everything's still time homogeneous. And so if the distribution on y is sort of the same at every time, because the marginal distribution, then you sort of in some sense mix together this what's happening over x, and the stuff over x is going to be the same over time. That's the intuition.
But if it doesn't depend on y, then shouldn't knowing x not tell anything?
No, it does depend on y. It does depend on y. But it doesn't depend on t.
No, but what if it doesn't depend on y? Would that still be?
Well, if it doesn't depend on y, then you've severed.
Oh,
Then you've severed this connection, and then you've got.
Okay. Oh, so okay. If it. All right.
So then basically it's a bunch of IID random variables. That are stationary by definition, right? IID. So okay, I'm not going to. I don't think I'm going to prove that here, but what I want, I'm probably going to add that as a homework problem tonight. So when do I change that to probable homework problem? It's something you should think about. It's a good problem. However, what we want to do is compute the entropy rate of x. And we're not going to compute the exact entropy rate of x, but we're going to compute upper and lower bounds, because they're going to be much more manageable. So the upper and lower bounds are going to be the following. Actually, if we look at the following quantity, which is the entropy of xn given x1 through xn minus 1 through x1, well, that's also equal to the entropy of xn plus 1 given xn through 2. So we're, again, assuming things are stationary. And now we can condition, so the first equality is based on time shift. The second inequality, let me mark this off for the YouTube listeners. The first equality is due to a time shift. The second inequality is due to conditioning reduces entropy, because now we're conditioning on x1. And then the third, this inequality is due to both time shift and an additional conditioning. And essentially we keep doing that, and that's going to be always greater than the entropy of the Markov chain. So that's a very simple upper bound. Just conditioning on the current one given all of the previous ones. The conditioning is the upper bound. Now, lower bound is going to be given by conditioning, additionally conditioning on the first Markov chain variable y1. So the question is, why is that a lower bound? Well, let's start by looking at the entropy of x7 given the previous x's up to but not including x1 and also y1. Now, that's equal to this. Now, can I ask someone to answer me why that's equal? Why, in other words, why is this equality true?
Because y is.
Think about that graph. So I'll draw that little piece of the graph. So we've got y1, x1, y2, x2, da da da. And we've got yn, xn. So we're looking at the entropy of this guy given all this guy, all this stuff here, and this guy. So, but in other words, xn is independent of x1 given y1 and x2 through xn minus 1. And if there are things that are conditionally independent, I can add them, I can further conditioning on them in a conditional entropy quantity, and that doesn't change the conditional entropy since they're irrelevant. So I can either add them or remove them. I can add, if they're independent, conditionally independent, I can remove them. And if they're not there, I can add them without changing the quantity. Okay. Now, for the same reason, maybe someone can tell me why this equality is true. Same reason, right? All of this stuff over here, get something you can see. All this stuff going back into the negative time territory is irrelevant because I'm already conditioning on this stuff here. So anything into the past, y0, x0, da da da, anything is separated in the graph, so I can condition on that. And then similarly, for the exact same reason, I can further condition on the x's. Now here's where I start bounding. So now I sort of increase, I remove things that are not conditionally independent. In fact, what I've done in this inequality is removed the y's and conditioned only on the x's. And then, thanks to stationarity, I've shifted up. And voila, here's the lower bound. This then is a lower bound on the thing we want.
Why do we need the second step?
Which one?
Second step, 817.
817? So what we're doing, sort of the first inequality in 816, the equality in 817, and the equality in the unnamed equation are sort of adding things to what we're conditioning on that are really conditionally independent. And so we're sort of expanding the set, and then we're going to remove things to get an upper bound. So to get 817, we're adding the additional y's, right?
And then remove them from that. Right?
And then removing them, that's right. We're adding them, keeping inequality, but removing them is going to give us an upper bound. It's going to move up.
The upper bound is only given, it's actually a result of removing y1, right?
That's right.
So my question is, why do we need the y0, y minus 1?
Because we want to essentially get the bound in this particular form. And so this is the final thing that we want. This is for n plus k plus 1, but basically this is true for any n, k, and 1. So we're just adding that in order to remove it, so to sort of go back in time. And we could change the indices and do it differently, but this is a valid way of doing it. I'm not saying that this is the only way of doing this, but this is a valid way. So here's the summary of the upper lower bounds on the entropy of a Markov chain. Hidden Markov model. So great. The other thing we have is this ever-shrinking sandwich theorem, which basically says that as n gets big, the upper and lower bound approach each other. And the way to do that is to look at the difference. And immediately you can see that the difference corresponds to the definition of mutual information. So it's the definition of mutual information of the mutual information between xn and y1 given this history, because they all have the same history. Right? It's the additional, so if this doesn't make sense, we're both guys are conditioning on this stuff, on the green part. And then we've got this new thing, which is yellow, and then xn here. Hopefully that makes it clear. You know, it's too bad, when you look at the YouTube video, you'll see the colors much more saliently. They're much, I mean, on my screen they look great. So we're conditioning on the same thing, so then the green stuff up here is really just sort of some other stuff. It's just conditional mutual information. So we get the conditional mutual information. And we know that that's, from the definition of conditional mutual information, no greater than the entropy of y1. Right? We also know that this value, from the definition of regular mutual information, is no greater than the entropy of y1. Right? So now if we take limits, the limit in this case, well, we use the chain rule of mutual information here, which is equal to this sum here, which is less than or equal to the entropy of y, which we know from assumption is going to be less than infinity. So we've got essentially an infinite sum which is a constant, which means that if we've got an infinite sum which is a constant, then it must mean that the terms go to 0 as n gets big. And hence, since the terms go to 0, each of the terms is essentially this difference, so that difference must go to 0. Okay. So, so summarizing, while these are upper and lower bounds, if we take limits, then we actually get exactly the entropy rate of the stochastic process of the observed values of the hidden Markov model. Okay, so this is actually as good a time as any to take a break, because we're going to move on to the next topic, which is coding, and that will be getting into chapter 5 material. So are there any lingering questions on entropy rates of stochastic processes or anything that we've spoken about?
For the hidden Markov model, if we know y1, it means that x2 and 3 is independent with x0 and x1 is 1.
Yes. It's conditionally, the right way to think about it is it's conditionally independent. But I mean, I usually like to be careful about that kind of wording, because I always try to say, this is conditionally independent of something else given something else, you know, because it's very different than just independent. But yeah, that's right. Okay, let's take a short break. Okay, so I guess during the break, there was this one thing that came up during the break was the last problem on homework 3, and I was saying that I think everybody should spend a long time on that homework, and given it due tonight, that's going to be hard to do. To be honest, I would prefer that people turn it in late and spend a long time on that last problem than to turn it in on time and do that problem superficially. So, if you want to like do an update, should we make an extension for? No, maybe we shouldn't do that. If I do that, then I'm going to be seen as a softie. So I don't know. What do you think, Mr. TA? What's that?
We can extend.
You want to extend it or you don't want to extend it? Well, I'd only want to extend that one problem. Okay, so I will extend that problem to is due tomorrow, but all the other problems are due tonight. Okay? So that means that it will be marked as late, but our TA will, if the first 10 problems are not done tonight, they will be marked as late. The second problem you can upload as secondary PDF file, just the last problem. Is that okay? Okay, so let's talk about coding. So, we talked about Shannon's first theorem, which basically said that there exists this block code that has vanishingly small probability of error. But now, Chapter 5 really gets into the issue of, well, what about practical codes? Right? Codes that we can actually build, codes that we can actually do something. And maybe it's not necessarily universal code, because maybe we want there to be some probability distribution. Shannon said that, okay, well, if we know the entropy of the source, we don't even need the probability distribution. We can just sort of code for what happens. And the only thing that happens are the things that are only going to need the coding for, and they're going to be the typical set, and there's only going to be 2 of the NR possibilities. And we don't need to know the probability distribution. But that's not really a practical code. Those were sort of block codes in the sense that we need to get a big block. So if we have a random source, even if it's IID, we need to wait for a big giant block of them before we can actually say, okay, now I know what that one is. Here's send this code word for that block and send this code word for that block. What if I don't want to wait that long? What about streaming codes? Imagine if you wanted to watch a movie on Netflix and you couldn't start watching it until you received the whole download. So therefore there'd be a big delay. But we'd really like the sort of codes that, variable length codes. On the one hand, like each symbol symbols might have a different number of bits per symbol, rather than say, like for example, in the block length code, we have a big block of symbols and we send this number of bits, and we can only essentially say that the number of bits per symbol is R. But that doesn't mean that each individual source symbol some symbols have fewer bits and some symbols have more bits. And Huffman coding will do that. And then the other thing is, like I said, sort of streaming codes where we can actually start coding right away. So that as symbols come in, as source symbols come in, we start sending out bits right away, rather than waiting for the whole source to come, which is obviously critical for things like internet streaming of digital data, or real-time telephone communications over a cellular channel, or any form of real-time or semi-real-time communication, Skype or Google Hangouts, or any of these forms of real-time communication, where you still want to compress, obviously, because you don't want to send more bits than necessary, but at the same time, you don't want to suffer from the latencies associated with long block codes. And so some examples of these, which I think we'll talk more about arithmetic coding next quarter, or maybe this quarter. But those are 2 examples that we'll eventually talk about. Limposiv, by the way, is actually a universal stream code, because it doesn't require knowledge of P. But for right now, we're going to essentially assume that we've got, we're going to allow ourselves to have knowledge of P. And we want a practical coding algorithm that can still approach or achieve the entropy limit. And we might use P of X. Okay, so we're not assuming that we don't have that. And that's okay, because we can, in many cases, either P will be given to us or we can estimate it in some way. We're not going to talk about how we get P of X. Like one way would be to look at samples and assume ergodicity and sort of estimate. There's a whole field on parametric and unparametric density estimation, which could itself take us several quarters. But let's just assume that we have either P of X or some approximation of P of X. And what we will do is see what kind of penalty we pay if we have an approximation. If we, instead of P, we have Q, we're going to see what kind of penalty. And the penalty we're going to pay is in terms of number of bits. Like how much worse will we do? And that, as I said last week, I think, will be based on the KL divergence. Okay, any questions on the overall? Okay, so a source code is a code for a random variable that basically takes, it's a mapping or function that maps from the domain of the random variable to a set of strings. So D star is like finite strings from D array alphabet. So if this isn't clear, then D star really is equal to, the set D, comma, D times D, comma, D times D times D, comma, dot, dot, dot. We're just not saying how long it is. Okay. And for every source word, or every, we're going to have a length, which is L, which is the length of the code word corresponding to X. Here's an example. Let's say it's a binary source. X is red, blue. And so we might then code into binary. So D is 0, 1. And we might say, okay, well, the code for red is 0, 0, and the code for blue is 1, 1. It's a very simple coding function. Okay. And the expected length of the code is just going to be the average length. So in the above case, the two lengths are both 2. So in that case, the expected length is going to be 2. So in general, we can actually use any D array alphabet, but often we're coding into binary. So much of the time, D is actually 2. Here's another example of a code. This is, let's say that X is 1 through 4, and D is, again, binary. So let's define a code with the table. So we have X, the source symbols, which are given by the first column, the corresponding probabilities, which are given by the next column, and then the code words, which are given by the final column. So this is a code that basically says the most probable source symbol, which is the source symbol 1, has probability 1/2 and has a very short code word, which is 0, whereas one of the least probable, or the two least probable code words, like 4 and 3, in this case 4, has probability 1/8 and it has a long code word. So this is probably the right idea, right? Because low probable things, you want to have longer code words. High probable things, you want to have short code words. And that's the best way, essentially, to get a short expected length. But before we actually get into even that idea, we need to sort of make a bunch of definitions. In this particular case, by the way, so the code word is, the entropy of this probability distribution is 1.75. So that's the entropy. We know we can't do better than 1.75 from Shannon's theorem. And this particular code word, this particular code happens to have expected length 1.75. Not bad. Here's an example of where our rate, which is the expected length, is exactly equal to the entropy. Okay, so this is one where we can actually achieve the entropy, exactly. And we don't even need to use a long block. But notice that we've used the probability distribution. So this is as good as it gets for this particular case. Another thing that's nice about this code is that it's relatively easy to code. So what source symbols correspond to this string? 0, 1, 0, 1, 1, 1, 0, 1, and so on, whatever. So you tell me. So this is going to be 1. I can't write as fast as you're saying. I don't even have my pen selected yet. Okay, 1. And what's the next one? 2. So I'm going to put little commas here. And 1, 1, 0 is 3. 4. What comes next? pretty easy, right? We just sort of march along, and we somehow by this code we can actually punctuate it by just looking at the code. It's in some sense self-punctuating, or maybe we just got lucky. I don't know. Let's find out. 1, 2, 3, 4, 4, 3, 2, 1. Did we get it right? Yeah, I think so. And here's the punctuation. Code is self-punctuating in some sense, or at least it seems to be. It was strangely easy. Well, is it? Is English self-punctuating? Well, in that case, can you read this? I can read this because I can rotate my iPad. What about you? Try reading that. I think you can kind of do it. How long does it take you to read this sentence that is written without any punctuation marks or even end of sentence marks, such as a question mark or even intersentence spaces? Okay, so what about the word? What does that say? Nowhere? Or does it say now here? There's ambiguity, right? So English obviously has tons of ambiguity. Nowhere could be now here or nowhere. I mean, it depends. Nowhere. It could be a question, or you could say now here. Okay, so I mean, English is not self-punctuating. Here's the actual instance of this, just with punctuation and with spaces. And you know, the curve thing is sort of meant to sort of act as a little bit of a disturbance. But you know, it's definitely easier when there's spaces in English, and certainly unambiguous for things like nowhere. So other codes, I mean, codes have exactly similar properties. So let's say that X is 1, 2, 3 again, and we're using a binary code word. So here's our code. The source symbols are 1, 2, 3. The probabilities are 1/3, 1/3, and 1/3. And the code words are 0, 1, 0, and 1, 1. So in this case, the expected length is 1.66, and the entropy is 1.58, and we're greater than the entropy. So that seems okay. I mean, it's not optimal, obviously, but it's not, doesn't look too bad. Can we easily decode? So I have the answer here for some reason. So what would 1, 0, 1, 1, 0, 0, 1, 0 be? You shouldn't have, I don't know why the answers popped up. But, so this is also pretty easy. What about Morse code? Everybody remember Morse code? Morse code is a series of dots and dashes. Here's the dots and dashes for Morse code. The most frequent letter is short with one dot, like E is very frequent, and so it's got one dot in it, whereas other, say, not so frequent things have long codes, like Q is a long code word.
Oh, the space.
Yeah. You need punctuation.
I didn't hear what you're saying.
You need punctuation.
Yeah, it sounds like it, because E and F are prefixes of each other, or E is a prefix of F.
Yeah, and E, and you can't differentiate between threes and...
E's got all sorts of funny things. So it uses a binary alphabet, basically, you know, dots and dashes. So, you know, this is interesting on the one hand because, first of all, this code was developed almost 200 years ago now. It gets the idea that, you know, very probable things should have shorter code words and very improbable things should have longer code words. But maybe it's not so easy to decode. It wasn't written at a time when people understood coding theory and had the full wealth of thought that has gone into information theory over the past 60 years. So here are some other examples of code. So again, we've got a series of source symbols, probabilities, the corresponding entropy, which is this, and we've got 4 different code words for them. So the one thing is to note is that we've got these different expected lengths. So the entropy is 1.75. We're not going to do any better than that. We have code set C1, which has got an entropy of 1.1. Is that right? And there's a bug here.
Oh, but you use the same symbol for.
Yes, that's right. Okay, so it's not a bug. So the first code word has entropy that's lower than expected length that's lower than the entropy. But the problem is it's got a problem. Actually, we'll go through these. I think let's just go through these in general. So the code efficiency is basically the entropy over the expected length. Okay. And which code is best? Let's look at each one in turn. So the code with the shorter expected length is usually preferable. So which would we prefer? C1 or C2? Well, maybe we wouldn't prefer any of them, because how can the expected length be smaller than the entropy? So the problem, obviously with C1 is that this code string 00001 could come either from this set of source symbols, or this set of source symbols, or this set of source symbols, because it's in some sense it's not uniquely decodable. We can't take a series of code words and come back to a set of source symbols uniquely. So you might actually be perfectly happy with such a code if you're willing to acknowledge that you've got errors. And then in some sense, lossy compression does exactly this. Like when you look at the JPEG standard, or if you look at MP3 files for music, or if you look at any lossy compression scheme, any voice compression scheme, you don't have everything about the original signal. You have distortion. Is this distortion acceptable? You can actually achieve the entropy rate lower than the entropy if you're willing to accept distortion. And that gets into this whole notion of rate distortion theory, which we're going to talk about at the beginning of next quarter. And that's where you look at the trade-off between the rate, and as soon as the rate goes below the entropy, you start experiencing some distortion. And as the rate goes farther below the entropy, the distortion goes higher and higher and higher. And there's this underlying trade-off. And there's this notion of achievability, and there's achievable rate distortion pairs and unachievable rate distortion pairs. And it actually makes sense to talk about that there. But here we're actually not talking about that. This code may be undesirable, so we can't decode. This is probably a bad code for this particular one, because we've got very high probable symbols, 1 and 2, or relatively high probable, that have the same code word. So that's going to be probably bad. So how about code 2? How do we decode 0011? So every code word is unique, right?
It's not self-punctuated.
It doesn't seem to have the self-punctuation property. So if we had a comma between every code word, then we could do it, right? However, putting commas is going to increase our rate, right? So it suddenly means that each code word is now 1 bit longer, or 1 comma mark longer. Maybe we'd have to use a ternary alphabet, 0, 1, and comma. That's going to increase our rate, and you can bet you that increased in rate is going to boost us above the entropy rate, right? So in this case, we have the same problem. So it could either be 1, 1, 2, 2, or either 3, 5. So we can't decode without a probability of error. Actually, what I should do, this would be good, is like, we could have d is equal to 3. Namely, d is equal to 0, 1, and a comma symbol. which would increase the rate to be greater than or equal to the entropy. Maybe I'll add that to the slide. But you get the idea. Without the comma, we can't do it. What about C3? You know, this seems feasible at least, since the entropy rate is below the expected length. And decoding seems easy. When we have 111, 110, and 1010, we get 4321. It seems like every string encounter somehow seems to easily get to the end of a code word before getting to the next code word. Notice, for example, that no code word in C3 is a prefix of any other code word. 0 is not a prefix of 10. 0 is not a prefix of anybody else, because all the other code words start with 1. 10 is not a prefix of 110 or 111, since all the other code words other than 0 start with 11. And similarly, 110 and 111 are not prefixes of each other, they're unique. So it seems to have a prefix-free property. Now what about code 4? So can we decode this one? How about you tell me? Okay, so if we see basically only if we see a prefix like 0, 1, like for example, we don't know until we see more bits what that code word is. So for example, like we see let me just make this really, whoops, let me make this really clear. What happened to this? Okay. So when we're at the point, let's say this is a streaming code. So we've received all these zeros. Okay, we receive the 0. Do we know at that point what code word it is? No, we don't, because there's some common prefixes, prefaces, I should say. But then when we receive the second 0, we know that the first 0 is really a 0, because there's no code word 0, 0. And similarly, when we receive this 0, 1, we don't know until we see the following 3 1s, that in fact this guy is a 4 at the end. So we have to look ahead before we see something. And maybe that last one, maybe that guy ends up being a 0, and it's only when we see that being a 0 do we know, oh, this is a 0, 0, 1, in which case it's this code word. So these things, there seems to be some sort of strange interaction that's going on. So we're going to make this more concrete by defining different types of code. So a code in general is said to be non-singular if every element of X, the alphabet size, maps to a different string in D star. So in other words, that means that if these guys are distinct, if the two X's are distinct, then the corresponding code words are distinct. So we can view this as a mapping. So every distinct X, which corresponds to these guys here, corresponds to a distinct mapping. So there's no collisions. A collision would be if another guy maps to the same guy. So C1, the first code that we saw was singular. Right? It was a singular code. What about C2, C3, and C4? Maybe I have this table again. So do you remember? We'll look at this again. Look at it. I have the table. Yeah, so it's C2, 3, and 4 were not singular, but some of them had other problems. So okay, so I guess the idea of this next slide is to sort of say, again, our goal is compression. Send or store a sequence of code words for a sequence of symbols. And a non-singular code could become unique if we add commas between words. So Morse code is exactly that way, that we need to add some sort of space or timing. So it basically really, in some sense, has three symbols, a dot and a dash and a space. But what we want to do, and we've already sort of touched on these ideas, that we really want what are called self-punctuating codes, or also sometimes called instantaneous codes. Instantaneous because basically they're, you know right at the end of a code word that you've received that code word without having to look farther in the future or seeing a punctuation symbol. Because a punctuation symbol increases our alphabet size. We don't like that. Now what we want to study, however, is, for example, that seems like a limit on the set of coding schemes. Does being self-punctuating or instantaneous hurt us in terms of our rate? Another question to ask yourself now before I'll give you the answer. What do you think? I mean, think about that. Is that going to hurt us? So before we get into that issue, let's talk about a code extension. So in general, a code extension is when we sort of take a sequence of source symbols and concatenate the corresponding code words together. So it's a very simple concatenation operator. So in other words, this should really be a star here. Right. So no commas. Right. In other words, we're not putting a comma between each. We're not extending the set of symbols we're using in the code word. So in other words, if C of x1 is 0 and C of x2 is 1, then C of x1, x2 is going to be 0, 1. Just a bit string. So another code, so a code C with extension C star is called uniquely decodable if the extension is non-singular. So basically, if we now take a series of code words, a series of source symbols, and we feed them to our extended code, and then if every unique sequence of source symbols has a unique extended code word. Now we saw that, for example, C1 was singular. It was, even if we look at individual source sequences, both symbols, source symbols x1 and x2 mapped to code word 0, and the bit string 0. And extension, if we extend C1, of course that would also be singular as well. Right? Now C2 is also singular. I should say it's not uniquely decodable. I mean, the extension is singular. I should say extension of. But in general, the question is of how much we wait. So sometimes we might even have a uniquely decodable case, but we might need to wait until the very, very end of the string before we actually know what it is. And here's sort of a funny example of this. So consider this code. So we've got the source symbols, code words for each symbol. So it's 1, 0, and 0, 0, 1, 1, and then 1, 1, 0. Okay, this is a funny code, right? And forget about the probabilities. So is this uniquely decodable? Well, it's non-singular, right? Because every single source symbol has a set of different code word. Is the extension uniquely decodable? Is the extension non-singular, I mean? There's no real ambiguity. It is. What about this code string? So is the first symbol a 4 or is it a 3? Okay, so there's two ways of interpreting that. If you take this to be, a 4, let's start adding some commas. Let's assume it's a 4. So we do this, add a comma here. It's a 4. Then we got 0, 0, 0, 0, 0, 0, 0. Oh, what's that extra? What's that extra 0 at the end? There's no code with that. Sorry, I got to back off. Let's say it's a 3. There's a 3. and you got a 2, a 2, and a 2, and a 2. So if you, and now imagine, so in other words, whether or not there's an even or an odd number of zeros, it determines whether or not the first symbol is either a 3 or a 4. And imagine now, rather than there being 8 zeros, there's 80 million zeros or something. So you have to literally wait till the very, very end of the stream before you know the identity of your very first code source symbol. So is that a good code? Probably that's not such a great one, for obvious reasons. So this is really 3, 2, 2, 2, 2. It's not 4, 2, 2, 2, then something else. Whereas this is the same problem, right? So this would be 4, 2, 2, 2, 2, because there's going to be probably, I think there's 9 zeros there. Nine zeros here.
But aren't we wasting codes because we're using 2 symbols to encode 2? Or you could just use 0 or this.
Yeah, I mean, I'm not talking about the optimality of this.
I know.
But I'm just talking about that, the idea of uniquely decodable. So here's an instance of a code that's uniquely decodable, but it also has this other property, which is that we don't know the identity of the symbol until the very, very end.
No, I mean, what I was getting at was that if you have a code like this, does this necessarily mean that such a code is wasteful in some sense? Necessarily?
No, it does not mean it's wasteful. It just means it's hard to decode. So there's several, since what we want to do in this section is we want to talk not only about optimality, but this is really like a practical chapter. This is the first practical chapter. It's saying, well, you know, Shannon code, typicality theory basically gives us this sort of long block encodes. That's not practical. So now we want to talk about, you know, let's say we get access to P of X. Maybe we can do practical things, do practical coding. But there's still some other issues associated with codes, and we want to sort of come up with a set of properties of a given code, some of which might make decoding easier or harder. So we can still have a uniquely decodable code, and that seems like just unique decodability is not sufficient for practicality, irrespective of the optimality of the code. Because in general, the more restrictions we place on a code, the greater the chance in general we'll have of us eliminating the code that's optimal from the entropy, from the expected length perspective. Now what we would like, ideally, in the ideal world, we can find a code that is both practical, meaning it doesn't have this property. You know, might obviously uniquely decodable if we want to have no error. And we're talking about the lossless error context here. We want to have a code that's lossless, which means it has to be uniquely decodable, which means that for any source string we get a bit string, we can actually go from those bit strings to exactly back to that set of source strings that were compressed. But at the same time, you can say, okay, well, what if I prove to you that, okay, we can actually come up with this code that achieves the Shannon rate, but it has this property that you have to wait till the very, very end of the string before you actually know what the first symbol is. That wouldn't be so nice. That's not a very practical code. But it turns out we're going to see whether or not that's the case. I have a picture in a minute that sort of shows you a little bit. So we're going to have a little bit of another definition. So this is called a prefix code or an instantaneous code if no code word is a prefix of any other. And once, you know, since we're essentially going to get to a prefix, and since we get to the code word, the end of the code word, it can't be the prefix of any other. We know that there's no ambiguity. So in this particular case, in this code here, we don't have that property because 1, 1 is a prefix of 1, 1, 0. So this is obviously not a prefix code because 1, 1 is a prefix of 1, 1, 0. Whereas a prefix code wouldn't have this property down here. It wouldn't have this property that we need to wait till the end of the code string before we find the identity of the earlier symbols, source symbols. Because as soon as we reach the end of each code symbol, we're done. Right? So I already said that. So a prefix code then is sort of naturally self-punctuating. there are implicit punctuation marks between the code words, and those are the fact that we get to the end of the code word, and it's not a prefix of anything else. And so therefore, a prefix code means it's uniquely decodable. But as we saw in the previous example, a uniquely decodable code, that one where we need to wait till the end before we identify the first symbol, doesn't imply it's uniquely decodable. Sorry, doesn't imply it's a prefix code. Uniquely decodable doesn't imply prefix code. So here's our set of codes. So we have this big oval, which is all possible codes, right, which includes the arithful codes. The non-singular codes, right, those are the ones where every source symbol gets its own code symbol. Now, the non-singular codes are the ones that we can always decode without an error as long as we add a punctuation symbol, right? So Morse code is like a non-singular code. We have the uniquely decodable code where we don't need to have a punctuation mark, but it's not practical because we may have to wait a while before you figure out what the identity of the earlier source symbols are. And then last, we have these instantaneous codes, which basically are prefix-free. No code word is a prefix of any other code word. And the set of instantaneous codes is smaller, of course, than the set of uniquely decodable codes, which is smaller than the set of non-singular codes, which is smaller than the set of all codes. Now the question is, where do the optimal codes live? Do the optimal codes, now what we mean by optimal, we mean the optimal error-free codes. Do the optimal codes live here? Or do they live here? Or do they live here? In other words, most importantly, are there optimal codes that live here? Because if there are, then that means that there's no penalty in terms of expected length in choosing only instantaneous codes. That would be great. And that's what this question is asking. So we might think that we want to use codes only from the largest possible class, namely the non-singular codes or something. And obviously, this isn't generally true. In an optimization, so you're trying to optimize over a space. If you increase the space, as long as you find the optimal point within that space, you can do no worse than when you optimize over a smaller space. However, a bigger space might have undesirable properties, number one. Number two, it might be harder to find a good code in this bigger space. So if we can limit the space to be as constrained as possible while making sure that there's still a good solution there, you can do better. Okay, so we've already said this last point. Okay, so it turns out we're going to be able to show, I don't know, this is a spoiler alert, but we're going to be able to show that there's no, well, actually, I think I've already spoiled it, but what do you guys think? What do you think will be, do you think there'll be a penalty associated with expected length when we restrict ourselves to instantaneous codes? Well, actually, the idea is that, remember, the instantaneous codes are less complex, right? Because they're instantaneous, they're easy to decode. Like as soon as we get a code word, we say, got that symbol, another code word, got that symbol, another code, got this. There's no issue. Like the other code word we saw, where we have to wait till the end, we have to memorize the entire string and sort of store it in memory. And in some sense, that would be unbounded memory. Imagine a stream code that does that. We have to wait, we have to store the entire string, wait till we get to the end. Once we get to the end, we have to go back and start decoding from the beginning, which means memorizing the entire string. And instantaneous code means you don't have to do any memory at all. As soon as you get a code word, you pop out the symbol. Then another word, pop out the symbol. It's fast, it's low latency, low memory. It's great. So computational resources-wise, the instantaneous codes are the best. That's what I mean by practical. These are real practical considerations, like computational and memory considerations. Well, that's what I'm asking you. Is that going to get? Is that going to? Okay, I agree. It doesn't seem to be necessarily true. Now, it turns out that there's some good news in the world occasionally, and this was one of the instances where the news is indeed good, and we're going to show by looking at the craft inequality and a bunch of other properties that that within the space of instantaneous codes still lives optimal codes, meaning that you can compress down the entropy. So that's the good news. So let's start on that quest. The first theorem we need to show is the Kraft inequality. Now this is something, Kraft was an information theorist, and he had a master's thesis. He did this for his master's thesis. And his master's thesis was much more influential than his PhD thesis. This happens sometimes. You put all your effort into your master's thesis, and then you have this great discovery, and then your PhD thesis is a flop. It happens occasionally. So for any instantaneous code over an alphabet size D, the code word lengths must satisfy the following inequality. So remember, D is our alphabet size, and when we sum over I over all code word lengths, the sum over I of D to the negative Li is going to be less than or equal to 1. And this is an instantaneous code. And then conversely, if we have a set of code word lengths satisfying the above inequality, so all we need, and this is really, really powerful, all we need to ensure instantaneousness is that the lengths satisfy this inequality. You don't even need to know the code words. All we need to do is find lengths that satisfy this property, and that means that there can be an instantaneous code. So that basically suddenly turns it into potentially a mathematical optimization problem. Now, another thing that important thing to clarify is that this is saying that if we've got a set of lengths with that quantity, that means that there exists a code that's instantaneous. It doesn't mean that all codes with those lengths are instantaneous. It just means that there exists. But it turns out it will be easy to find it. Actually quite easy. So the key point of Kraft is that if we have these lengths that satisfy it, then since also, as we'll see, it's easy to actually find a set of code words that satisfy those lengths that are prefix free, no further restriction. I guess, let's say, assuming that we can actually find these lengths, what this means is that, which is actually going to be the key trick, we might as well use a prefix code as long as it's the case that we can actually show that there are codes with these lengths that satisfy this inequality that are also optimal. So this is sort of a critical step on the way of connecting instantaneousness and optimality. Because maybe if we can say, okay, well, are there codes with these lengths that are optimal, number one, and if we can do that, and secondly, can we take from these lengths and produce instantaneous code, can we do that? Then suddenly we've shown that instantaneous codes are also optimal. Because the optimality of a code is only a function of its lengths and its expected length. Right? So that's basically the idea. So how do we prove this? So we're representing a set of codes on a D-array tree. It's not necessarily balanced. And maybe if you've been thinking about the prefix code in the binary case, you notice that basically all we're doing is finding leaves of the tree. And so in the case of D-array, basically we have the root, which branches into D. The array is D, so at each step we branch into D, and each step we branch into D. So the code words correspond to leaves of this tree. So somewhere down here, after we branch, we've got a code word. So the code word basically means, this would be 1, and maybe D, and then this, and this, this, and this. And so we would sort of traverse. We'd take a path from the root of the tree down to the leaf, and that would give us our code word. And that's that statement. So a path from the root to the leaf determines the code word. And the prefix condition basically says that all of the code words correspond to leaves. So we don't get to a code word until we get to a leaf. So it can't be the case that, for example, this is a code word, and then there's some descendants that are also code words. Like this and this can't both be code words. So we would have to, in some sense, restrict it so that the code words are only at the leaves. And we're going to get kicked out of the room soon. So let's just prove this. So let's say that L max is the maximum length of the longest code word, or is the length of the longest code word. So let's now expand the full tree down to that depth. So now we're essentially saying, like the tree, maybe we have originally an imbalanced tree, and so these code words are here and here. But now let's expand all of these lengths down here. So some of the nodes corresponding to, so some nodes at that level, so some of these vertices, I should say, at this level of the tree, are either code words themselves, like this guy's a code word here, or they might be descendants of a code word. So if, for example, this is a code word, and this is a descendant of code word here, or they might be neither. So like, for example, this guy here is neither a code word nor a descendant of a code word. So now consider a code word at level I in the tree, so it has length of L of I. Then just looking at the combinatorics, I mean, when we in order to get its descendants at the tree at level max, basically at the next level down there's D descendants, and then the second next level there's D squared descendants, and going on and on from that particular code word at level I, Li, all the way down there's D to the Li, L max minus Li, total descendants. So every code word that is of length Li has D to the L max minus Li descendants at depth L max. And we've got this prefix condition, which is descendants of code I at level I are disjoint from descendants of code J at level J, when I is not equal to J, right? So descendants of different code words are disjoint. And the total number of nodes in all sets of descendants is certainly no greater than D to the L max, right? That's sort of the total number of leaves in the balanced version, in the completed tree. Right? So there's, in the first level there's D, the second level there's D squared, and all the way down to the end there's D to the L max, possible vertices at the end of the tree. So what this implies is that if we sum over all code words and then take the number of descendants altogether, we're going to be less than the total number of descendants at the end. And so this is going to give us Gauss inequality, because we just divide out D to the L max. Okay, so we're going to have to end today's lecture in the middle of this proof, unfortunately. But we're going to start up on Thursday with Kraft inequality. Are there any questions? Okay. Yes, question?
Yes. So if prefix codes correspond to a tree, what would the weird code with the global dependence be?
Well, you could still think of them as a tree, but where code words can lie anywhere. In other words, non-leaf nodes might correspond to a code word. Okay. So let me.
Can that be non-singular?
It can be non-singular. We saw instances of it being non-singular. So and it can be uniquely decodable.